Okay, everybody, so I'm going to move ahead to the fusion activity, and there's lots of parts in this, so I'm going to talk about it a little bit. The first part is just a few questions, but the idea is that you're going to look at this article and this video first. Now, I couldn't put this video into the playlist because it is a New York Times video and not a YouTube video. But I did place another YouTube video that's a little bit longer and a little more detailed, tells you a little bit more about it, into the playlist ahead of this video. So maybe you've watched it, maybe you haven't, but I want you to be thinking about that. As you are watching those videos, as you are doing the readings, I want you to think about these 4 questions. First off, what did you learn? It's just the basic. Secondly, where do most of our heavy elements come from? So this is the important thing that we're thinking about. These elements like gold, like uranium, large elements like that. Where do they come from? How do they exist? And would this suggest that fusion needs a lot of energy or releases a lot of energy? And why do you think that? And then again, would these resources suggest that fusion is natural or unnatural? That's the question that's on there. I want you to think about what it means by natural or unnatural. So think about that and go ahead and answer those questions. The second part of this activity is a lab that we would have done in class, but it's one that you can do at home. You can use really anything for this lab. So if you've got something like the 15 white marshmallows or the 15 gummy bears, that's great. A, it's great because you can eat them. B, it's great because they stick together pretty well. So you can mush the marshmallows and the gummy bears together and they hold together in the nucleus, which is fairly important for this. If you want to use something like beans, if you want to use something like Legos, like whatever you have that you would like to use for this would be great, as long as you have like 15 of one thing that can be protons and 15 of another thing that can be neutrons. So here's what we're going to do first. We are going to do candy fusion. So gummy bears and marshmallows. Gummy bears proton, marshmallow is the neutron. So look at these. You've got hydrogen 1, hydrogen 2, and hydrogen 3. Reminder, when we talked about isotopes, they're all hydrogen because they all have one proton. That's the thing that determines the element. But the isotope of that element is determined by the number of neutrons it has. And the number for the isotope, hydrogen 1, hydrogen 2, hydrogen 3, that number is the mass number. So hydrogen 1 has a mass number of 1 because it's only got one proton. Hydrogen 2 has a mass number of 2 because it has one proton and one neutron. Hydrogen 3 has a mass number of 3 because it's got one proton and 2 neutrons. So, thinking about that. Now, the next thing you're going to do is you're going to create 3 identical atoms of helium-4. And then we're going to use those in the next step. After you've done that, sketch them out, hang on to them, don't eat them yet, until we're going to smush all of the helium atoms together, all 3 of them together, to create a new element. And I want you to count up in that nucleus that you just created by smushing those 3 helium atoms together. How many protons do you have? How many neutrons do you have? How many electrons do you have? Or, sorry, you don't need to tell me about electrons. I don't know why I said that. I'm getting so used to talking about atoms. Protons and neutrons, protons and neutrons. That's the focus we want to think about. So what element is it? Appropriate symbol. Here is how we would do the appropriate symbol. The symbol notation is like this right here. So you've got the 2 and then the hydrogen. So you can do this by thinking about, as you're writing, you can think about the superscript, which is right here, if you want to click on that, if you're working online. And that'll put it up high into like the exponent type thing, and then you can write and then you would click that off and write the symbol for the element. Okay, You can also think about writing the isotope name of it, so helium-4. When you do this you're thinking about your element. Think about the element, make sure you're writing the mass number as well. You're going to draw the element, how many protons there were in all 3 helium atoms, and then how many are present in the 1 nucleus you have afterwards. How many neutrons were present in all of the 3 helium atoms, and then how many were present after the reaction. You're going to go through this and you're going to make another helium atom and smush that into that big nucleus you already have. And so do that with the candies, draw what you get afterwards, label it, and then you're going to do it one more time, one more helium atom, and smoosh it onto this gigantic nucleus that you are building. And for this here, I want you to write these symbols of the elements in here. What did you start with? The helium atom, and what did you get after you added those together? Think about how you could form magnesium from the element that you have right here. What would you need to add to it? And then finally, moving on to the analysis. Thinking about nuclear fusion, you want to think about the total mass numbers. Mass numbers, remember, is the number of protons and neutrons together. So how does that affect the mass numbers before the reaction and after the reaction? Then same thing, does nuclear reaction affect the total of the atomic numbers? Remember, atomic number is the number of protons. When it says site-specific evidence to support your answer, I want you to go back to something you did and say, oh, so when we did this, this was the number of protons before, this is the number of protons after, this is how I know this answer happens. In the normal function of stars, iron is the heaviest element formed. So most stars, when they are doing the fusion in the stars, they don't make anything heavier than iron. And so I want you to think of a fusion reaction that could produce iron 52. All right? Really? There's a ton of different correct answers you could give me for this. So I want you to think about what do you think is most likely, and what is something that just works. Those are the important things. Is energy absorbed or produced by nuclear fusion? Think about where it happens. Nuclear fusion, we're talking about happening in stars, right? Do stars absorb energy or do they produce energy? And then what are some limitations of using candies as a model of fusion? This is kind of an open question. I want you to think about it, and we'll go from there. All right, I am going to go ahead and end this video here, and that's about that.